right, let's get started. So a few announcements just so we know where we're at in the schedule. We're almost to the end. And so this week we shuffled stuff around, so we'll be doing our aspirin synthesis. So that should be a really fun lab. I like it. It's like an actual OCHEM lab, and you will make actual aspirin that you could take. Not that I would recommend it. You want to check its purity. And so then next week, so week 9, like I said, we'll have our kind of impromptu ice cream lab. And so like I mentioned, we'll have, some supplies just to make regular ice cream, milk, cream, sugar, all that. But then if you wanted to bring, like I said, any other types of milk, dairy-free milk, or chocolate, whatever concoctions, feel free to do so. And we'll compare ice cream methods. And then, like I said, week 10, poster presentation. So don't let that sneak up on you. If I can spell. So if you need help, right, ask help now, especially with printing your poster. Get help kind of early. And like I said, I can at least help you print to a color printer here at school, but unfortunately that's the only services I can provide. And I can help, like I said, just use those templates online, the PowerPoint one, or you could use another one. Just make sure that it's kind of set for the correct dimensions. And then I'm a tad behind on grading, so I'll catch up on your class probably between now and Thursday. Work through that grading. And other things, so I'll give you your exam probably week 9, end of week 9, so you can have it all of week 10, and probably try to turn it in like the Friday of week 10 if that's possible. All right, so now let's look at our last chapter in our book here. And so our last chapter is transition metal chemistry, but I feel like it's also just like a survey of random stuff, because transition metal chemistry is obviously pretty broad in itself. And so the book kind of takes us through this tour. Actually, before we do that, I wanted to bring up, I forgot, I had pulled up some stuff. So I don't know if y'all pay attention to the news at all, but we'll say an aside here. And the only reason why I brought it up is, well, A, it was on the news, but it was talking about a type of compound that we had briefly mentioned. And so here is the article. And of course, the other reason why I wanted to bring it to your attention is it's like so impossible to have a discussion about chemistry in the mainstream media without like everything being sensationalized one way or another. And so of course, what caught my attention, well, two things caught my attention, was the fact that the compound in question was azodicarbonamide. And so if you remember, I don't know if you remember or not from our OCHEM chapter, we had kind of discussed these azo compounds. And if you remember those azo compounds, they tend to be used in like coloring. I think methyl red we had looked up last week is an azo compound. So remember, azo just have these two little nitrogens bound together. So very broad class of compound. And I had mentioned that usually they're considered somewhat toxic. And they always have like these weird colors. So this one in particular is yellow, which I did bring up a picture again just to kind of give us context of what these compounds look like when we work with them. So that's what it looks like, this azodicarbonamide. And what caught me, though, is of course they call it a yoga mat chemical, which is like always a frustrating way to discuss chemistry because I don't know what the heck a yoga mat chemical is. And obviously they're just trying to be scary by calling something a yoga mat chemical. So it's used in the yoga mat production. It has to do with the breakdown, and it makes gas, and it helps make the foam fluffy. It's also used as a bread additive, so that's where the concern was. And so, of course, they were discussing trying to pull it. And again, it's one of those things where I don't know, but let's kind of look at the chemistry, right? So the concern is these two chemicals that it breaks down to semicarbazide and urethane. So let's look at those. And I couldn't find too much on this chemical, at least toxicity-wise. So that was something that, you know, we could dive into. So there's been a few toxicity studies on it. And I think that was maybe where some concern was. I don't think this chemical had as much concern as the other one. But again, when you try to study something and whether something's carcinogen or not, it's always difficult, right? Because they tend to feed these rats way more than you would ever get in your lifetime per weight. So again, make of it what you will. And so then the other compound.
It's kind of like feeding a dog chocolate and calling it poison.
Exactly. It's just like, and of course, you know, they use rats since they're supposed to metabolize things similarly to humans. But yeah, you kind of have the right thing. It's like, you know, the dosage makes the poison. So, you know, it really is difficult to tell. And so the other chemical in question is this one. So again, depending how you want to name it, ethyl carbonate or urethane. And so what's kind of interesting is this is a naturally occurring compound. So if you look at it, and well, actually I found a few interesting statements in the Wikipedia page. So it starts off mentioning that the Japanese used it as a co-solvent in some of their medical injections. And they went on about like how carcinogenic and terrible this was, but then they don't talk about whether this was actually studied. So I'm kind of curious to like look into this to see if anyone did ever study it. So that was kind of weird. But then the other thing to realize is this is a natural byproduct in a lot of fermented products. And so it mentions that the fermentation process tends to make anywhere from 15 parts per billion to 12 parts per million of this compound. So if you're eating fermented foods, you could potentially be exposed to this. Again, right, going back to, is it carcinogenic or not? I don't know.
They also said it was a bread additive, but it could also just be a natural byproduct of like sourdough.
Yeah. So again, if it's a natural byproduct of fermentation, so it's always convoluted, but yeah, I think they do add the azo compound potentially to breads, and then again, it does decompose. And so ethyl carbamate is considered a group 2 carcinogen, so that means possibly carcinogenic. And then it does mention that, you know, certain cultures that obviously eat a lot of fermented foods naturally, you know, could be exposed to that. But again, it doesn't like go on to discuss the health effects because, I mean, at least anecdotally, I thought those cultures were considered to have good diets. So again, going back to the carcinogen effect, is it, you know, how much? Again, you're not like eating this pure compound. So as usual, it's hard to know how toxic something is or how carcinogenic it is, but I at least wanted to point that out in the news there. All right, so now we're back to hodgepodge transition metal chemistry. So right, we're looking at the middle of the periodic table and all the fun stuff it can do. And so your book just, again, kind of gives a trivia overview of everything. I kind of included some cool reactions. And so we're going to get to this in a second of how we can basically treat the metals. Well, actually, I'll give you a preview so it makes sense. And so basically we have these numbers here, and we'll kind of recap the electron configuration issue. But basically we can just treat scandium like it has 3 valence electrons. So again, right, 2 in the 4s2 formally, 1 in the d, but it really behaves as a d3. And so looking at that, that's what happens here. So this is just a starting material. And then just kind of appreciating how to put ligands onto metals. And this is kind of cool. Again, just kind of appreciating the different compounds that these things can make and bind to ligands here. So again, you see a lot of nitrogen-based ligands. And then what's also cool is, so in this one, they're doing some nitrogen chemistry. So trying to do nitrogen fixation, which we should back up just a little bit and talk about why all these things kind of, why we care about nitrogen. And so I pulled up our nitrogenase catalyst. So of course, nitrogenase, these are enzymes, right, that fix nitrogen naturally in the soil. So like legumes and plants like that are known to be nitrogenase, or like maybe you've heard of plants that are called nitrogen fixators. So those would be plants that could do this readily and naturally. And so again, right, the chemist doesn't care about this complex biological structure. What the chemist cares about is the active site. And so a lot of research is done trying to do like heterobimetallic catalysts. And there's been a lot of like iron sulfur chemistry in an attempt to kind of mimic this reactivity. And so that's why people kind of, choose the scaffoldings that they choose, and again, why they're trying to bind nitrogen. So again, right, going back to like the Haber-Bosch process, that's very energy intensive. So if you could be like your nitrogenase catalyst and do it at ambient temperature, obviously that would be good.
Do you know if the Haber-Bosch process can be done with, it's typically done with physical impact in high temperatures?
Yeah, it's just high temperature and pressure on the industry scale.
Can it be done electrically, like with a capacitor or something like that?
I'm not too sure, but either way, like if you're passing electricity or heat, like that's an energy intensive process. So either way, yeah, it's using a lot of energy, and I don't have the exact figures, but like a lot of the world's energy goes into the Haber-Bosch process. So again, that's why everybody does a lot of research on these nitrogen fixation catalysts. And so then kind of, again, just looking at our survey. So moving on to titanium, which is next to scandium. And titanium dioxide, this is another one of those substances which, is it toxic, is it not? I don't know if you remember in the news, it was in the news like last year, I think, about Skittles. Anybody remember that? Well, see, there goes the mainstream media. No. So it was just last year, they were making a big scandal. Oh my gosh, there's titanium dioxide in Skittles, and titanium dioxide is so poisonous. I mean, again, it's like one of those who knows. So it is in Skittles. It's a common food additive. I thought it was considered generally safe. And now that I looked into it with the Skittles paper, I really couldn't find any evidence that said that it was toxic, so I don't know why the Skittles thing took off. And titanium dioxide, so it's famous for being in sunscreen, and so this is considered like some of the best sunscreen, either titanium dioxide or zinc oxide. Yeah, and of course both of those work the same way, by creating a physical barrier. And obviously they're very white, right? So that's how they work. They create the physical barrier. But then if it's very white, that's also why it's used in food. And I've seen it used to dye like vegan cream cheese. So I've seen it in there as an additive, again, to help kind of make it really white and nice looking. So again, it's a white powder. And I've also seen it used in like water purification for like simple systems. So it's kind of used as a coagulant, so you can, you know, mix some titanium dioxide with your water, and then it should settle at the bottom and kind of take out large particulates. And I think it's fairly effective. I know there was research done on that. And then again, just kind of looking at a survey of chemicals. So I think this was from your book. It included this reaction, and I'm not sure why it included this reaction. This is a pretty nasty reaction if we think about it. So this compound, this is also called tickle, affectionately by chemists, because it is what we call a box killer, meaning it would kill your glove box. So it's pretty reactive.
What do you mean by glove box?
So I think I mentioned those things before. It's like the NASA looking stuff where you would do chemistry. Let me pull up a picture. So these things, so chemists use them if you're doing like air sensitive chemistry. So a lot of transition metal chemistry that we're talking about would take place in a glove box. Yeah, and so if you sometimes, like NASA has them obviously to keep the space samples protected from oxygen, and same sort of thing.
They're used for like radioactive chemistry too.
Probably not good enough for radioactive chemistry. It's very difficult to work with radioisotopes because you wouldn't be able to work with a positive. So most glove boxes operate under positive pressure, but then you can't have like radioactive isotopes because it'd be pushing out those radioactive isotopes.
You do like an atmosphere like xenon or something?
Not even xenon. It'd have to be a negative pressure atmosphere glove box. And so those are difficult to set up because it has to be right enough pressure to keep the air out, but then have somewhere to vent it. So yeah, it's a pain to work with radioactive isotopes. Yeah, there's a lot of regulation. That's why people don't do it. Like, if you want to do radioactive chemistry, it's like basically just the national labs. Even a lot of the old professors that I knew, they used to do like radioactive chemistry way back in the day. The regulations that you have to deal with, the training, the monitoring, like it just, people gave up. So that's a glove box. And so this tickle chemical would destroy this atmosphere. So this works, it has a copper catalyst to remove oxygen and water and keep it all happy. And so again, I don't know why this reaction was in your textbook, because it's a pretty nasty reaction. And I'll also say silicon tetrachloride reacts the same way. And so what happens, gosh, I should have realized this earlier. I should have pulled up a video if I can. Because this was potentially used in war. So it's hard to know which one they use, if it was tickle or silicon tetrachloride. But they tend to pour this compound out of a plane, again during times of war, and then it reacts obviously with water, and that means that it's going to react with water in the atmosphere, and it creates this wonderful smoke screen. Let's see. So again, this is kind of, we're not quite sure what chemicals being used, but this is essentially the idea. So if they're making a huge curtain, it's some chemical, probably, like I mentioned, titanium tetrachloride or silicon tetrachloride, and it's going to react. And so it makes this cloud that obviously they use it to shield and obfuscate. But not only does it create this smoke screen that is terrifying, but obviously look at the byproduct of this reaction. So hydrochloric acid. So if you were a poor soldier getting bombed, and right, you would be exposed to a bunch of acid gas, which obviously would not be good for your lungs. So yeah, wonderful reaction there. And again, this HCl is going to eat up the glove box if we're talking about a small scale reaction. But like I said, often used in wartime, unfortunately. All right, so then moving on to our next chemical. So your book just showed some solutions of vanadium. And so this is just kind of helping to highlight the amphoteric nature of vanadium. And so again, it just makes different complexes in different pH solutions. And so then chromium, again, we're just kind of giving some fun facts. And I didn't put any of the compounds like chromate, but your book mentions that it can be used as a bubbler, which is used to remove traces of oxygen from those gases such as nitrogen or argon. That being said, most people don't tend to use these bubblers anymore. That's only because usually you can buy what's called ultra high purity gas, and it's 99.999% pure, and this is for nitrogen. Oh, you wouldn't buy oxygen in that purity, but mainly nitrogen, maybe argon if you are rich. So then, right, usually not necessary to purify. And this works for extremely sensitive chemistry. So if only you had like a lower purity gas source, or for some reason you thought you had air in the line, but you'd probably want to fix your system. But yeah, so that's how you could, again, get rid of trace gases. So again, chromium can react with oxygen. Manganese is another one that will come up, and you'll see it probably in OCHEM in your future. So it's often used as a staining solution. So this permanganate solution is an oxidizing agent. And so going back to kind of our OCHEM, that means that it can break these double bonds, and it makes oxygen to them, or it could also attach the alcohol depending on the double bond. But again, basically this is used as a stain to find or elucidate double bonds. So again, this would be like a more advanced like OCHEM technique if you're trying to figure out what your compound is. Did you make a double bond or not? And then you would see, does it react with your oxidizing agent? And then obviously there's compounds of manganese, but again, we're just kind of taking a quick tour. Iron, I mean, I don't think we can say enough about iron. I think we've seen a few iron samples in labs. So of course, right, iron forms different compounds with oxygen, which again, I think you are learning and appreciating. Iron pyrite as well. So again, lots of iron compounds naturally. And then iron is, of course, of interest in research chemistry, and this is from the Peters group. I should have labeled it, but they were making a bunch of these tripodal species, and so they have this, what's called this tripod ligand, and this, I don't know why, but these like tripodal ligands work really well to stabilize different compounds, and they do cool chemistry. And so that's a pretty big deal that it is able to bind nitrogen. Oh, and then quick question. So right on the manganese staining, once it's oxidized, it's oxidized. So it's, that stain is like a permanent thing. So this is like a permanent transformation that happens, right? So you're like breaking the bonds of your compound that you're testing, even if it's in just like the little TLC plate. So back to iron, and so again, a lot of different frameworks, so carbon, boron, silicon, and then this is just kind of showing how, of course, they smelt iron, so this was in your textbook, and so everything just gets put in the giant furnace essentially and melted down, of course, to eventually get iron. See if I want to say anything else about iron.
Is that because iron is really dense?
Which part?
Because the iron sinks down to the bottom.
Oh, yeah. So this would be because it's dense. Yeah. So that's just like any sort of metal smelting. Yeah, it's going to come together. But iron chemistry is pretty, like I said, pretty popular. And so then again, just kind of fun fact trivia. So cobalt, of course, is known for its pretty colors, basically. I think your book mentions that somebody had like a cobalt cat statue or something that was all blue and pretty. And so, of course, obviously used a lot in ceramics and coloring, different pigments. So lavender pigments, again, more ceramics. They threw in here nickel cyanide as well, so again, that could be used for electroplating. Nickel's also a catalyst. Yeah, people like cobalt for the pretty blue colors. And then nickel chemistry. So people really try to do nickel chemistry. So of course, if you look at nickel, right, it's in the same column as palladium and platinum. And so a lot of people really try to force nickel to do some cool stuff. And I mean, it does make complexes. But again, some of the issues is palladium and platinum can do 2 electron processes, and nickel sometimes will just get stuck on 1. So that makes it not as great catalytically. And then copper. So of course, I think everybody knows that the Statue of Liberty is made of copper, and that it's green, obviously due to the oxidation that has occurred over time. And then this is just showing, again, different types of compounds. And so we have here a pentahydrate, which is blue, and then showing that you could heat it up, drive off the water, and then make the anhydrous copper sulfate, and that would be a white powder. And so you can't always just drive off either water just by heating. So you would want to refer to like a purification manual and see how you would actually do it. So sometimes you can remove the water by like refluxing in a certain solvent. So you might need something else other than just heat. And so zinc, again, not too much to say about zinc, other than we'll put in the zinc oxides for sunscreen. It also has other uses, mold inhibitors, and could be used in photography development, although I guess now everyone's digital.
The thing I know is it's used as a sacrificial anode in ships when it's underwater.
Yeah, so that's another, so sacrificial anode. And of course there's a lot of different coatings that they can use for ships too, like the iron oxide coating as well could prevent, again, both oxidation and I think the barnacles attaching.
How does it function as a mold inhibitor?
I think the zinc could disrupt some of the bonds. I would have to look into the mechanism, but I know like silver tends to attack like sulfide bonds, so I would imagine zinc might have a similar mechanism. And then so gold, what can we say about gold? I mean, obviously used in a lot of different things. So, right, gold is pretty. You can make pretty compounds with it. So, ruby glass, that's basically what it's emphasizing here. Also throws in some silver compounds. Oops, why am I making it wig out?
Gold is also used a lot in electronics because it doesn't corrode as much as others.
Oh, which one? Sorry.
It has like certain
Which metal? Sorry, I just didn't hear you.
Gold.
Gold, yeah, that would be true. Gold is just soft, so that's the only difficulty in working with it in like electronics, like you mentioned. And then, so silver iodide. This is again one of those compounds that I think is under the conspiracy theory umbrella right now. And I don't know if you follow what people talk about chemtrails. And so again, this is one of those ones like, yes, so it mentions it here, dispersing clouds to potentially induce rain. So again,
cloud seeding, though, that's not.
yeah, but then people are like really paranoid about that and like releasing silver into the air. And I mean, we could debate about the toxicity of heavy metals in the air. So again, like down the rabbit hole. And it also goes back to, again, like who's regulating the chemtrails, but
It's a little crazy because coal reactors release like 27 tons of radioactive material into the air every year.
yeah, I mean, again, it depends what you're worried about, because like radioactive isotopes tend to be kind of short-lived, but you know. Oh, and then so asking about like sacrificial metals, so usually they have to be electroplated on, and that will, again, it just acts as something to react with instead, or like coating. And let's see. Silver nitrate, I think I'll do a demo. I can't remember when, either next week or the week after, but there's a cool mirror plating demo. So it mentions this here, that silver nitrate is used in the manufacture of mirrors. And so we'll kind of see that. So you have a solution, it reacts, and then it literally plates silver. And so that's how you can make a mirrored surface. But I don't think they do that anymore to make mirrors. I'm not entirely sure.
That was done in like the Victorian era. It was like how mirrors used to be made.
Yeah.
Techniques.
Yeah, but it's probably still used like up until pretty recently. And other uses, so again, silver used a lot in photography development. Again, we mentioned, right, those silver compounds are light sensitive. And then mercury. So mercury, again, is always one of those sensationalized compounds. So elemental mercury, I don't think it's too bad. But then, like, organomercury compounds are super toxic. like, oh, we'll look at this one. So we'll look at that. But then some of these, like, you know, inorganic mercury compounds, a little more questionable. I mean, used to use it as a fungicide. Probably not a good idea to have mercury, you know, running around in the water and soil. But again, used to be kind of used more than obviously also used to be used in pigments, but I think a lot of those mercury compounds are toxic. All right, let's look at some other cool stuff. So looking at mercury, so let's look at this.
This video.
Oh, come on. Oh, fine. There's an embedded ad. Why is it translating it in Spanish though? Go away.
Has been sponsored by NordVPN. You can get a special deal and support the channel by visiting nordvpn.com/NileRed. Over the years, I've worked with Mercury.
So hang on, this is too long of a video. All right, so I know lots of you like Nile Red, so that's why I picked this. And so I just wanted to show the sodium and mercury reaction, but let me find the correct part here. So blah, 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 right? He's cut the sodium. His sodium looks pretty terrible if I'm being honest, but that's fine. And so I'm going to I'll let you watch the video and then I'll kind of criticize his technique because he does it a little different than I would have done it, but again, I didn't video myself, so.
Side of things. As I mentioned before, this reaction was apparently notorious for a lot of splashing, as well as flaming sodium. To deal with this, some procedures suggested just using a really large flask, but they were also doing it on a much larger scale. I figured that because I was only doing this with a few milliliters of mercury, a large test tube would probably be fine. So I poured in a random small amount of mercury, and then I pulled out my small piece of sodium, quickly dried it, and threw it in. I was kind of nervous that I'd immediately get fire in molten sodium, but nothing happened. The major reason for this seemed to be that the sodium was just a bit too tarnished, and it prevented it from coming into contact with the mercury. The sodium's also way less dense than the mercury, so it kind of just floated on top, which...
So that's where I'll pause, because this was a little funny to me that he added it in that direction, because when I've mixed this before, and I'll explain like why people do this, but usually I put the sodium metal on bottom, you pour the mercury on top, and then it makes like a little poof cloud. So I've never seen like fire or anything crazy like he said. But usually it's like a way to kind of clean the sodium, and then it also intercalates it so that you don't have just like pure raw sodium, but instead like a nice gentle mixture. But let's watch because he'll get it to go.
Didn't really help either. To fix this, according to some procedures that I read, it's pretty common to use something like a glass rod and to shove the sodium into the mercury. Then once it's underneath, it can be scraped and crushed to expose the fresh sodium. So I decided to try this, and initially I still had some trouble getting it started, but then suddenly there was a little thump, and all the sodium instantly disappeared. Then when I mixed it around a bit, I noticed that the texture of the mercury had also changed. The reason for this was because as the sodium combined with the mercury, it didn't do it uniformly. The reaction was extremely fast, and the mercury that was around the sodium took up most of it and got a relatively high concentration. And when the concentration of sodium gets above about 1% by mass in mercury, it starts to solidify. So what this gave me was a bunch of solid sodium amalgam mixed in with some regular liquid mercury. However, after I let it sit there for a few minutes, the sodium slowly dispersed evenly throughout the mercury, and most of the solid bits disappeared. It kind of went back to more or less looking like regular mercury, but the one major difference was that it was now sticking to the glass a bit. I then continued adding more sodium, but even the next one didn't result in any fire or sparks.
So yeah, we can watch it. But...
On my third run though, I used a slightly bigger piece of sodium, and I managed to get some fire.
Okay, now I want to see fire.
I couldn't find a good reference for exact...
So I've never seen that fire before, but like I said, I've only done this in a glove box, so that's maybe why I didn't get fire. Uh, but I just wanted to show you kind of how the sodium and mercury mix together. And of course, mercury, again, it's liquids, and then it kind of makes that weird mixture thing. And it's, like I mentioned, super useful. And you want about like a 1 to 5% sodium. And mercury is how it's prepared. So you kind of mentioned, you know, that you can only have so much sodium. And so, like I said, this is kind of used as a gentle reducing agent. And again, right, sometimes you'll learn that chemistry is like half art and half chemistry. So I don't really have a good explanation for this, just that when you put the sodium in the mercury, again, it kind of distributes it and makes it gentler. And so anecdotally speaking, I've seen this happen where, you know, a reaction may not work with sodium metal, that's just too much of a bomb or whatever, it's just too reactive, versus if you add it with the sodium and mercury, same mechanism, you're still using sodium as your reducing agent, but it'll work better over mercury for whatever reason.
Are there any compounds that form solution in mercury? Is a solution really something that can happen in a metal?
I mean, you could say this is a solution, right? It's just how you want to look at it. And people, you know, make all sorts of amalgams too, like gallium can do similar stuff. Like people put gallium on their MacBooks and destroy it and make like liquid.
Would it be considered an alloy at that point? Or?
Yeah, so then it's an alloy or like an amalgam,
Okay.
is what it's called too. And so now we'll look at the extreme. So methyl mercury is pretty toxic. And so I just wanted to show you this famous case that happened. And so this was actually an experienced chemist. I mean, she was a faculty member. And I'm not quite sure what reaction she was doing. This was a while ago, but she used a small amount of dimethyl mercury and then spilled a drop or two. So this is what's kind of scary about this, the organomercury compounds is, again, they're pretty toxic. And so even though she's wearing a glove, so the problem with organic compounds, like organic solvents, is even though we wear the appropriate gloves, it will still go through your glove. So if you, again, once you go to CHEM, if you get solvent on your glove, I would just change it, better practice. And, you know, again, don't really know what happened, if she realized that she had liquid on her glove or not at that point. But basically it was too late already at that point. So obviously she cleaned up. And this was in August of '96. And then basically she started having neurological issues. So blah, blah, blah. And, you know, she had very high mercury toxicity, so 800 times the normal level, and so she eventually, you know, died a few months later. So kind of interesting, again, right, not trying to scare you off from chemistry, but that's just the reality of different chemicals and different toxicity. But again, it's really those small compounds that tend to be toxic. All right, maybe we should take a break now. So we kind of finished the trivia-ish part, and so after the break we'll look at kind of the meat of the content. So starting to look at our d orbitals again. So yeah, let's take a 10-minute break. All right, so now we're getting into kind of the details, right? And we're going to be answering kind of the how and the why these transition metals do cool stuff. And so first, let's kind of compare, right, the ground state electron configuration. And so, right, if we recall, when we looked at our electron configuration before, we were just looking at kind of our gas phase transition metals. Again, right, they're not bound to anything, no connections. So that's where we got kind of this, right, electron configuration. So again, we could kind of review, and oh yeah, so titanium here would be 4s2 as we fill up, right, potassium and calcium. And then we said that scandium started 3d1 typically. So then of course that would give us 3d2. But then what we really find is that it behaves kind of more like so. So it's kind of total electron count, right? The S and the D, since like we mentioned, they're pretty close in energy level. And so, right, it mentions here, so now for complex transition metals, our D levels end up below our S levels, and so they essentially get filled first. So we'll get into, again, like the why and the how. And so this has to deal with the geometry, but basically once we start complexing these metals, then it changes the energy levels of our d electrons. And so again, we can just think of them as these metals. So scandium typically behaves as D3 or a 3+ metal. And that's typically seen, so we again saw those scandium trichloride compounds. But then, right, so titanium, vanadium, chromium, so they just keep going. So this would be D4, D5, D6, D7, so iron's D8. And again, all these numbers match on the periodic table. And so all that means is it can take oxidation states, right, anywhere from 0 all the way up to 8 potentially, or, you know, if it was nickel, 10, but not that you would see that. But again, just saying that it has that many electrons to give up or involve in bonding. And then if you look at, so it makes a statement about, so in group 11 and 12, right, they're generally kind of more stable, those d electrons. And so again, we kind of see them behaving typically as 1+, or zinc, right, is always 2+ typically. And sometimes you can see 2+ for, like I said, copper, but not always. And so copper is probably more difficult to work with, and gold, though, has been known to do, again, catalytic activity. So all the third row down here, these are, again, considered kind of more your workhorses for catalytic chemistry. And then people try to get the more abundant first row transition metals to do similar cool things. And so now what this is showing is basically how many d electrons. So it's comparing here. So it's saying, okay, if we have scandium 2+, then it's going to have 1 d electron. So again, it started with 3. So 3 minus 2 is 1. Same thing. So this is titanium 2+, showing you that it's going to have 2 d electrons remaining. And so it just continues. So again, right, all we're doing is subtracting the total d electrons here minus its oxidation state. So that's all that's trying to show. And obviously, right, increasing d electrons as we go down the line. And so then other things to note are our d orbitals. So this is our z squared. So of course, we care about these two a lot, and we'll look at these again kind of why as we progress. But we can just start orienting ourselves. So if we look at this dz squared, so of course this is formally on what we would call the principal rotation axis. So you could think about transition octahedral complexes to get you in the mindset. So I chose sulfur, but we'll look at other complexes. So starting with just a regular octahedral complex, later we'll look at metal octahedral complexes, but same sort of thing. So right, you have your sulfur and these two fluorines on this principal rotation axis. That means that when we look at metal chemistry, we're looking at the z squared is going to be involved in bonding. And then if we have an octahedral complex, then our x squared minus y squared is probably also involved in bonding. Again, you're just seeing how those ligands right now would line up, especially if we're looking at like a tungsten complex. So now we can kind of replace the sulfur with some sort of characteristic metal, again, like tungsten.
Does that count as an octahedral complex?
Yep, so it'd still be octahedral complex. And
Why
so,
is it called octahedral if there's 6 bonds?
I mean, this is the name of the geometry.
Okay.
And so again, we're going to be seeing how these two are involved in bonding. All right, so we saw this. And so again, this is just comparing our ground state configuration for iron. So iron metal, 4s2, 3d6. And then we see in a metal complex, iron is known as d8. And so in this case, again, we're getting there. But let's analyze this. And so if you remember CO, so let's draw out its Lewis dot structure, because it had a funny Lewis dot structure to begin with. So if we remember, CO has this Lewis dot structure, triple bond, and then, right, what's weird about it is, of course, if we were to put our formal charges on it, carbon would carry a negative formal charge, and oxygen would carry the positive formal charge, which typically kind of violates our rules, right? So if we remember, it's typically the most electronegative element that should carry the negative charge. But what's cool about this is now we can appreciate why CO tends to bind like so. And so what we have here is iron is in the center, and then notice these two electrons here. So those are primed to donate, and so that's what's going on, is carbon is contributing 2 electrons to this bond here. And so that's also why, so they put this D8 here, but we should clarify, so iron has contributed no electrons to bonding, right? And so for the inorganic chemist in me, I would call this a neutral ligand. So again, it's providing both electrons, so I can finish drawing it. Again, I'm drawing it in this way to show that it's CO that's contributing both electrons to that bond. Other terms we can use are dative bond. So So again, where it's one direction. And so we can also state that iron is in the 0 oxidation state. So again, right, it has contributed no electrons to bonding. So it has all 8 electrons still there present. So that's why it's still D8 formally. Does that make sense? So once we start adding ligands with charges, we'll see how the oxidation state changes too, which just goes back to, right, the charge balancing we've been doing, but we're just kind of getting a slightly deeper understanding.
Donates to electrons to the iron.
In this case, yes, but this is just for CO, right? So this ligand is special because it has 2 electrons there.
I'm seeing the iron's electron configuration is 3d6 and 4s2. Where do those 10 electrons go in the configuration?
So hang on. So right, you said 3ds, 4s2, but that's again for the metal configuration. So A no longer has this ground state, right? So now this is the ground state configuration.
Because it's an ion?
Because it's complex,
Okay.
right? So the difference, and maybe we should draw out the orbitals, right? So this starts off, and we have something like, oh, our 4s is right there, and then we have these degenerate 1, 2, 3, 4, 5 d orbitals, right? So this is, again, for a basic kind of metal. And so again, we have to fill up, oh, lowest one first, blah, blah, blah. 1, 2, 3, 4, 5, 6, right? So that's, again, for our ground state metal. The problem is, so now if we throw it into this configuration, right, these orbitals are no longer degenerate. And so, sorry, I didn't have this at the top of my head. So then when it splits to this configuration, again, this is now beyond our scope of our course, but it would look like this. And so, right, we broke our degeneracy of our d orbitals, and so that's why right now we fill the d orbitals instead of the 4s. And then, yeah, not quite sure how this would fill. So we'll get to that in a second, right? So assuming it'd be 1, 2, 3, 4, 5, 6, 7, 8. That's again kind of what I would assume, but we'll get into high spin, low spin, and all this other stuff in a second. So right now we don't even have enough info to determine this. I'm just kind of guessing. All right, does that kind of clarify the...
I still don't know where the electrons go, because if it has those 8 orbitals, those come from the 2 that are added to it goes from 6 to 8, those would have to come from the 4s orbital?
Yeah, so the 8 come from the 4s2, right? So that's just how many iron 0 starts off with, right? But then you could start getting into the 18 electron rule.
Do you fill a d orbital when you attach these?
No, we're not talking about p orbitals, or at least not right now in this context.
Okay.
And so then, right, we could get to the 18 electron rule. So this is where that comes from. So that's typically like for transition metals is where you see this 18 electron rule. That being said, the 18 electron rule can be the 17 and 16 electron rule and really anything else. But again, that's transition metal chemistry. And then so you would get 18 electrons from the 5 bonds. So 5 times 2 is 10. And then you have your D8 from your ground state. So this one would be a happy 18 electron compound. All right, so then this is trying to tell us, okay, right, for oxidized metals, so now oxidation just is saying we've lost electrons from our ground state. So again, right, this was our ground state, so 3d8. Now, if we've oxidized our metal, we've lost something, lost electrons, and it tells us again to subtract our oxidation state from our group number. And so again, all that is telling us is, well, now we're at iron 2+, so now we have 6d electrons. But then we can start to kind of, again, piece together where they came from, because we want to appreciate that and see that. Oh, sorry.
So when iron's in the D8 state, it doesn't have a charge on it?
Correct. Yeah, so that's, right, again, iron 0, D8. And then, so this is iron 2+. So now, right, 8 minus 2 gives us 6 electrons. And then what we are saying, so we can again analyze this bonding motif here. And so if we look at chlorine or chloride, right, if it's acting as a ligand, well, let's just draw out our Lewis dot structure for chlorine. And so how many electrons does it have here? How many bonds does it like to make? So what do you notice about that? How many electrons does it have versus the CO?
That's got 7.
7, but then how many to participate in bonding, right?
It's got 1 space left over compared to iron.
Yeah, so it just has 1. And so other terminology, again, this is kind of like beyond the scope of this class, but sometimes this is referred to as an X-type ligand, which just means that it only has 1 electron, so it needs an electron. So that's where the electron went, right? So we said we oxidized our metal. Well, we have to kind of bookkeep where it went. Well, it went to each of these chlorines, right? And then y'all can figure that out from, again, just balancing the charges that you know that, well, chloride tends to have the -1 charge, but now we're just kind of re-emphasizing and re-explaining this all. So, okay, since chlorine only brought 1 electron to the bonding party, iron was forced to give one of its d electrons to this bond here, and then obviously another one to this bond. Now if we examine, right, these nitrogen ligands here, we would find that they're actually dative. So I don't know if that's evident or not, but just kind of pulling them off. So right, looking at nitrogen, so it has 3 bonds here, so it has to have 2. And so this is very common for these nitrogen ligands to act as, again, what's called L-type. So donating 2 electrons, stabilizing our iron there. That kind of make sense?
Okay, yeah. Are we mostly going to be examined on the iron complexes and the iron bond behavior? Or?
No, I mean, we're just looking at iron because we're looking at the D counts, right? But like, so looking at this, so we want to be able to determine what's vanadium's oxidation state, D count, and maybe total electrons. So let's do total electrons for this one before we try these other complexes. So looking at this one, and so again, how you would analyze kind of total electrons on our metal. So we would start with our D count here. So we have now I'm worried I might confuse y'all. So I'm going to count it a weird way. So iron has 8, and then chlorine, again, I'm counting it by one method, so they're just doing 2 electrons each, so 1 each, 2 chlorines, and so we have and then we have 6 from our nitrogens, so this would be a 16 electron complex.
So you start by counting the orbitals in the...
So you always give it however many it has. So when you do the total electron count, so iron brought 8 to the party always, chlorine only brought 2, each nitrogen brought 6 to the party.
I see.
So this is, there's different methods of counting electrons is a problem.
But you're only counting the valence electrons?
Yeah, so you're only looking at, again, what's attached to iron. So you would say this is a 16 electron complex. All right, so see if you can try that with, like I said, these examples now down here. So we want, if I can make some space here. So we want our oxidation state of our metal. And then our D count. And then if we can, this total electron count on the metal, we may need to go through more examples of that. Ah.
Let's say OH2.
Yeah, it's just a way of writing water though.
Okay, that's what I thought.
how are we doing? So I'll kind of sketch out our compounds. So these are all, right, hexa-aqua compounds, pretty similar. And so I think you noticed that it was trying to show that it's bound at the oxygen. So again, kind of think about what that means. Of course, our water has 2 lone pairs, so obviously one of those is involved in bonding. So I'm trying to show that by drawing it funny. And so 1, 2, just trying to draw all 6 on there. And so all these would be considered, right, 2, donating 2 electrons to our bond. And then we don't have any chloride ligands, but we do have this 3+ charge to account for. So then what is our D count on vanadium? Or you could also give me its oxidation state. So based off of this, so what's vanadium's charge?
Its configuration is 3d3 4s2, but on its own it would probably be 3d5.
So 3d5 for
So you're
the,
gonna behave like iron. I don't know.
yeah, so they all, right, so we don't want to put anything in the S anymore. So the ground state is 5, right? So D5, but then if this compound has a 3+ charge, what's vanadium's oxidation state?
Does the 18 electron rule apply?
And one step at a time, because first we have to figure out, right, how many electrons it still has, because all we determine is that vanadium usually has D5, right? But then what's the charge? And water's neutral, so water has nothing to do with it.
It has 5 valence electrons.
Yeah, but then it's in a 3+ oxidation state, so what does that tell you?
It has a +2 charge, -2.
So then it would be, yeah, so vanadium 3+, right? And then what would that do to the D count? So it was at 5, right? Lost 3. What does that leave it at?
2.
So D2. So vanadium 3+, D2. And so now we could practice our total electron count. And so again, this one, I want to count it by what's called the neutral ligand method. And so that means I'm going to give vanadium 5, even though, right, I'm going to account for this charge in a second. I'm just trying to be consistent. And then 6 waters, so each of them bring 2 electrons to the party, so that's 12. But then we have the 3+ charge, so -3. So 17 minus 3 gives us to 14 electrons. So what you said, 18 electron rule always applies, right, except when it doesn't. That's just transition metal chemistry.
Does it apply here?
Again, it does and it doesn't, right? So like,
Apply here.
you're gonna kill me, man. But it's 14 electrons, right? Like I'm telling you, it's always ideally 18, but then it's not, right? So like there are so many exceptions. That's the problem with chemistry. So that's why I keep telling you, it's the 18 electron rule that's really the 17 electron rule that's really the 16, 14, right? You can get 19.
So because it's 14 electrons, it doesn't apply.
I mean, if that's the way you want to phrase it in your brain, yes. But I'm telling you, right, the goal is always 18. But this is chemistry, right? So, like, there's all sorts of binding motifs. People are trying to make different stuff all the time. So even though it is always the 18 electron rule, you're always going to find violations. So let's try. So then the next one is the same concept. So we're still practicing with these neutral ligands. And again, the only difference is now we're moving down the line. And so you could give me either manganese, its neutral count, and then figure out what oxidation state it's in from this charge. Then the D count. So based off of our charge, so what's our oxidation state of manganese?
4. That's 4 electrons.
So D4.
Yeah.
So D4. So again, looking at our periodic table. So okay, manganese are neutral, 3D7. And then you got 4, since we have a 3+ charge. Again, there's no other ligands to balance this charge with, so manganese has to be 3+, D4, and then again adding up our electrons. So I got lazy with our oxygens there, but again manganese brings 7 to the party neutrally. So then again, this is the neutral ligand method. And then each water brings 2 again. There's 6, 12, and then our 3+ charge, just like before. So then now we have 16 electrons. Questions on this one?
What should these numbers in the oxidation state?
3+.
It's the same as the chart.
In this case, because we have neutral ligands, right? So we had nothing, there's nothing else to take into account.
Yeah, if that was OH minus, it would be different.
Right. So then, you know, you'd have to balance it just like we've been practicing. And then, so the last one of cobalt. So again, similar, right? These are all pretty similar complexes, except what's our oxidation state of cobalt? What's its D count?
9.
So D9 normally, right? So then if it's 3+, it should be D6. And then again, we can count our electrons and compare. And so now cobalt, like we mentioned, is 9 neutrally. Each water is 2 again, times 6, 12. But then our 3+ charge, so -3. And so that one gives us 18 electrons at least. So now we can feel happy about our 18 electron rule. And so while we stare at that, so I'll just kind of show, this is supposed to be a crystal structure of this same compound of the vanadium 3+ hexaaqua cation. But I feel like there's more waters and other things complex. So I'm not sure. I didn't really read the paper, so we'd have to see like what other maybe counter ions are in here. But I'm just trying to show you the basic structure. So we have our vanadium at the center, and then you can again appreciate how the water is binding to it. You can barely see those little hydrogens. Hydrogens, they tend to not show up anyways on X-ray diffraction, and so people just kind of fill them in potentially based off of where they should be. It's impossible for me to know what they had to do, if they did that or not. Like I said, we'd have to look at their raw data, which we're not looking at right now. But I just wanted you to see what a crystal structure is too. Again, this is super important for inorganic chemistry, of like getting the actual picture of the molecule so you can actually do analysis on it. All right, questions or anything?
I know that hydrocarbons can be turned into PFAS chemicals by removing the hydrogen and replacing it with fluorine. If you have a complex sort of neutral molecule like vanadium with 6 waters on it, can you replace the hydrogens on there through processing with fluorine to produce a chemical, or does it not work like that?
Probably not. I mean, yeah. It's usually not that easy.
Carbon's uniquely stable too, so.
Yeah. Plus it's just like, yeah, it's different chemistries, how they kind of behave. But usually if you were to just blast like a metal with fluorine, it would just, you know, make a bunch of fluoride complexes. Lost my notes. Oh, did I skip this compound? I did. Okay, so I didn't mean to skip this one. And so again, this is just trying to show how we make metal complexes, basically, and what this outer sphere, inner sphere ligands mean. So again, this starts to get into a little more detail. And so kind of what the convention is, and what you may start noticing, is you have this whole part in bracket. And so this part in bracket is showing like what's actually complex to the metal. So meaning, right, like there is a bond, or a covalent bond, we'll say, right, to our metal here. So again, physical bond. And then notice that the sodium here, and they're showing it to you by, yes, it disassociates in solution, but all we're saying is that the sodium is outer sphere. So it's not really in the crystal structure of it. It's right, it's hanging out over here, floating around in solution. So it doesn't really matter. And so that's kind of a distinction you want to at least start making and appreciating. And so then obviously there's a lot of ligand substitution reactions. So again, kind of depending on the type. So these are pretty interchangeable just because they are both L-type. So if we were to draw out, obviously, the Lewis dot structure of ammonia, we would see it has 2 lone pairs, right, which it can donate. Also a base, right, we remember that about ammonia. So again, it has a tendency to donate those electrons. And so pretty colors, trying to remember how detailed on this we go. So we'll get back to the pretty colors. Basically, I mean, there's a lot of different things with the colors. It helps us to kind of understand the energy differences, which we'll get to, and kind of why they're different colors. So again, that all has to do with the splitting, which we're kind of getting to. So at least just appreciate the different colors. So obviously, right, this could be useful spectroscopically to track species. And I don't know, this is also why people like transition metal chemistry, is like, yay, pretty colors. And usually they make nice colors. Like I said, if you make poop color in chemistry, that's usually a bad sign. It usually means you made an intractable mixture, is the official way to describe a bunch of poop in chemistry.
What does intractable mean?
Intractable just means cannot be separated. And then, so question, just trying to, I'm not sure if I understand the question, but basically when we look at these different ligands, we have to examine like how many electrons they're donating to. So it's not just like how electronegative is, it's like how they can bind. But okay, so yay, pretty colors. All right, so now let's discuss how to name them, at least. And so like we've been looking at, so our coordination compounds often contain a complex ion, so basically some sort of ligands attached to our metal, and then perhaps a counter ion, so like we're seeing with that sodium, or again, you could have an outer sphere chloride or any sort of other anion. And so we'll get to the naming, so blah, 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 cation and anion. Cation is named first. All right, so some examples here. So let's kind of break this down. So looking at our compound, right? So this is really a nickel hexaaqua compound, right? We could abbreviate it as some sort of nickel 2 plus. Kind of similar to the ones we were just doing, right? So we could kind of rewrite it like this to give you a different context. But now they've rewritten it in a way such that we see our outer sphere ion. So right, we have chlorides. So these are not attached to the nickel. And so now we can name it. So of course, again, we're just balancing oxidation states. So we know chlorines are -1. So then, right, our nickel has to be in a 2 plus oxidation state. And so now we can name it. Again, we don't have any cations like before, like in going back to this picture, right? So we had a sodium cation, but we don't have that here, okay? So we just have an anion, and so then we can name it. So ligands are listed first, and then we can use our prefix. So hexa to say we have 6 water ligands, and of course water is called aqua. So hexa aqua nickel 2 chloride. And so now looking at this one, again, similar scenario. So we have our outer sphere bromide ion. And so again, telling us, just balancing our charge. So it looks like copper is going to be in the 2 plus oxidation state. Remember that ammonia is a neutral ligand, donating 2 electrons. And then just look at the funny spelling. So again, I'm not too much of a stickler for spelling. We have a double M there for amine, for our amine ligand. So hexaamine copper 2 bromide. Again, hexa saying we have 6 of our amine ligands on there. And so then in this case, what happens if we have 2 different ligands? So list them alphabetically. So again, right, break this down. So this is actually complex, right? So there's only 6 things complex, so this is interesting. So now let's take kind of a deeper analysis. So right, we have this nitrate. So this is outer sphere. So there's 2 nitrates just running around. And then again, we still need to find our oxidation state by balancing it overall. So even though we have this mix of, right, we have 2 anions or outer sphere, 1 is inner sphere, cobalt will still be 3+. So again, just balancing our charges there. And then now we can name it. And so ignore the prefixes, right, when you list them alphabetically. So we want to start with aqua, so penta aqua, and then chloro, so we don't need to say mono. So penta aqua chloro cobalt 3 nitrate. So any questions on that? So again, you just want to make sure you're recognizing that this has 6 things attached to it, right? That the nitrates are floating around just in solution. So you can kind of appreciate how they're drawn.
So the brackets sort of imply that there's a complex there, and that everything outside the brackets is like an association with that complex, but not necessarily attached to the central ion.
Correct, yeah. And so again, we have our prefixes if there's more than 1 ligand. So di, tri, tetra, penta, hexa, and then going on. And so then sometimes you get to weird scenarios, such as this one, which is a fun compound. And so looking at this example, so for example, when you already have a prefix denoting a number, such as ethylene diamine, so the di already says that we have 2 amino groups, so we wouldn't want to say di-di, so then we might have to use these prefixes. So if you were trying to use ethylene diamine and there were 2 of them, you might say bis ethylene diamine. And so you have bis, tris, tetrachus, pentachus, and hexachus. And so a good example of this is this ligand, which we can pull up a picture too, but we can decipher the name. So this is a pretty common starting material actually, because it's a palladium 0 source. So I've actually worked with it.
Are we going to be expected to memorize the prefixes?
I mean, your notes, your exams are open notes, so.
Okay, yeah.
So then breaking this down, what it's saying, so right, we have our palladium 0 here, and then, so before we get to this tetrachus, so we have a triphenylphosphine, and so all that means, so phosphine, triphenyl, so remember the phenyl groups are going to be your little benzene rings, essentially. So this is 1 triphenylphosphine, and then obviously you would have more, so PPH3, oops, sorry, too many P's. So now I'm just kind of abbreviating. And then right, tetrachus, meaning there are 4 of those triphenylphosphine groups there. So that's what this would look like. And so again, this is the compound, tetrachus, triphenylphosphine, palladium. And then, so we have, of course, other ligands that we haven't looked at, and obviously they're could be more. You can also, right, make your own ligand. So, right, again, one day you can make your own fancy ligand, name it whatever you want, and people will have to follow your abbreviation. So, right, we have fluoro, chloro, bromo, iodo, cyano groups are pretty common, hydroxo, nitro, nitrito, thiocyanado, isothiocyanado, so those are also common, carbonato and oxo groups. And again, you can notice that these, right, are charged ligands, so most of them are bringing, right, 1 electron to the party. And then these neutral ligands, again, tend to bring 2 electrons to the party. So amine, aqua, our carbonyl and nitrosyl groups are again kind of most common. Although we should have thrown phosphines into there. There's a lot of phosphines. Oops. Or I'll just call it PX3 for phosphines. All right, so I think we're starting to run out of time. So for Thursday, we'll keep kind of practicing naming and looking at these compounds. So again, we'll just kind of take a look at more binding motifs and look at our isomers. So I brought my molecule kits, but then we didn't get to it today. So we'll look at those different isomers and continue with crystal field theory. All right, so I'll have to post the notes. I haven't done that, but I'll get that going. And then otherwise, I'll see you in lab then. So just let me know if there are other questions.
Question about this. This was a while ago. This is chapter 24. I got stuck on this specific part here because these seemed easy because you're taking oxygen away from the equation. And I don't understand how in an acidic solution you can have oxygen introduced.
Well, I mean, you just got to go through the balancing, though, right? Because if you're in an acidic solution, you balance the oxygens with water and then add.
So you put oxygen on the left side, so that'll be 3H2 over here. There's 1,6.
Well, those are balanced.
Yeah, so would OH go on the left or the right? Or, no, it would be H3O, wouldn't it? It's hydrogen.
But it looks like your oxygens are already balanced, aren't they?
So is that it? Or?
I think so. I think it looks fine because you don't need to add any water because you have 6 oxygens, 2 sulfur. So yeah, that looks
Okay.
fine.
What about this one on E?